Ma vedi, incredibile. live.
Okay, so let's start this last lecture. So in the previous lecture, we focused on some predictions that are enabled essentially by the use of soft theorems because are focused on gravitational radiation that is in the soft regime, so whose frequency is, let's say, much lower for the case of a scattering of two objects with velocity v and impact parameter v is essentially lower than this ratio, which is the typical frequency around which instead the reference spectrum is peaked. Instead, today we are going to try to go beyond this soft, so this will be the soft regime. And instead today we are going to stay in a regime in which this parameter, sometimes it's called the U in the PN literature, this is a generic generic parameter, and so we are going to try to calculate radiative observables. In particular, we discuss a bit the waveform, and again revisit the emissions of energy and angular momentum beyond the soft approximation. So in fact, I thought just to begin with the gravitational waveform. Which is really the fluctuation in the metric that is sourced by the scattering of our two massive objects. Keep in mind that we're sending in a massive object like this. They reflect, and then in the meantime they also emit radiation, which in principle can be picked up by our interferometry experiment. And in fact, the basic setup will be the one that we already introduced last time or a few times ago, which is based on this KMOC idea of calculating expectation values in the final state out, which quite generally is predicted by acting with the S matrix on the in state, which we wrote down in some detail a few times ago, and it's just a way of modeling these two incoming objects with some well-defined impact parameter and some incoming velocity. So the relevant object to calculate the waveform is going to be the expectation value in this out state of the canonically quantized graviton operator. I'm going to write in this way. And okay, here A mu nu is a shorthand for sum over physical polarization of A, say, helicity times the polarization tensor, or you can think of this as being written down in some gauge, for instance, the Donder gauge in which the various components are independent. It doesn't matter as long as we in the end project over the physical polarization that we care about. So you remember this capital H for us is the canonically normalized graviton field. So in order to relate it to the metric equation, so really the metric minus the Minkowski metric, we have to remember to multiply by this normalization factor to 2 pi g, and this is going to denote liquid H mu nu is really the metric fluctuation, so dimensionless. And as you can see by this formula, the basic ingredient that enters this object is the out expectation value of this, say, the annihilation operator. So let's give it a name. Let's call it W. Sometimes this is called the wave shape for a reason that will be apparent soon. And in fact, let me also multiply by an I, again, for a reason that will be apparent in a second. So, again, what happens in analogy with what we already discussed for the impulse is that, of course, we will need to rewrite this out in terms of S in, and then the expectation in will essentially introduce the Fourier transform that we already discussed a couple of times ago. So the basic statement which we essentially need to do as an exercise is to show that using the fact that we are calculating a classical observable and using the definition of this in state, okay, let me remind it, recall it just very quickly. Basically, the product of 1 and 2 with one given by a phase space integral over the mass shell, theta minus P10, d P1 over 2 times a wave packet that you can take the sharply pitched around the physical momentum P1, which by a sort of short of user notation I also call P1 without making a big distinction, times the Fourier transform factor that places the object at a given impact parameter. Just a reminder. So the exercise is that you can show that if the operator that you care about satisfies property that all the amplitudes involved in this quantity do satisfy, so combinations of amplitudes satisfy. So if you take the sandwich between the relevant operator and this plane wave state that enters these Fourier transforms, what happens is that just take out the momentum conserving delta function times a function, which is denoted again O. Then you can, so the exercise is to use this property to show that in O in, so including now all these Fourier transforms and wave packet, in the classical limit is nothing but with the Fourier transform B1, B2K. Let me maybe draw a picture to remind me of the convention that we are using for this now 5-point kinematics. P1 and P2 are of course incoming momenta, P3 and P4 are the outgoing momentum of the massive particle, and K is momentum of the graviton. And conventions are defining Q1 as P1 plus P4, Q2 as P3 or P2 plus P3. And now, in contrast to the elastic case in which Q1 was equal to minus Q2, of course, Q1 plus Q2 is equal to minus K. Q1 plus Q2 plus K equal to 0 is a rewriting of this momentum conservation, right? And perhaps let me also recall the Fourier transform, which, as I mean, already appeared a couple of lectures ago, but say for well, I've been writing this of AT, O tilde, doesn't really matter. For any function that a function of Q1, Q2, and kappa and K, sorry, you can write it down in this way. It's just the natural generalization of our transform, but now taking into account this additional kinematic dependence. Of course, Q1, Q2, and K are not independent. You could choose to solve for one or the other, depending on convenience. And I guess the only key property they want to emphasize is basically the Fourier transform in the transverse space orthogonal to P1 and P2, but with an exception. And now there is a dependence on the longitudinal modes via this via the fact that here we have Q1 and Q2. So the K, for instance, the K dependence induces also some dependence on the longitudinal component. So along, say, P1, because you can rewrite Q2 as Q1 minus K. So you see that Q1 dot Q1 is not 0. It must be equal to minus Q2 dot K. So for instance, if you solve for it to eliminate Q2, you see the Q1 will not be exactly orthogonal to P1 and P2. It will only be orthogonal up to a piece that is proportional to K. All right. This is it. Maybe the only other notation I want to introduce is a notation similar to the barred variables that we had some time ago. You remember, instead of working with P1, P2, Q1, Q2, and Q, it was convenient at some point to use some sort of average, which makes discussion of loop integrals a bit simpler. So we want to define a similar notion here. So if one can define P1 bar as minus P1 plus half Q1, and similarly P bar to, and one can then show using the mass shell conditions that P1 bar is exactly orthogonal to P1 and P2 bar is exactly orthogonal to Q2. But of course, the inverse is not true. P1 bar dot Q2 is not zero, it's again proportional to something of order k. So in fact, the invariant, let's say, good to keep in mind what are the invariants that one can define. Of course, there is our beloved sigma or gamma, which is minus Q1 dot Q2 divided by M1 and 2, which will differ by the same quantity with P1 bar and P2 bar by order k corrections. And then one can define two sort of frequencies. Okay, P1 dot k divided by M1 and P2 dot k divided by M2, which are the frequency of the graviton as seen from the rest frame of particle 1 or as seen from the rest frame of particle 2, of course. And okay, the two invariants would be, say, Q1 squared and Q2 squared. Or you might want to choose Q1 squared and Q1 dot k, for instance, whereas of course k squared is equal to 0. So these are the five invariants that you can be. Very good. Maybe one last remark. I'm not sure if I'm going to need it anytime soon, but there's a nice identity that is very easy to show. If E is the frequency, is the total energy in the center of mass frame, and omega is the frequency of the photon as seen from the center of mass frame, then these satisfy this identity. More or less by definition of what this symbol means. But again, this I leave it to you as an easy exercise. Okay, so with this out of the way, let's go back to our objective. Our objective was to calculate this this beast over here. So I introduced this symbol for the A sandwich over there, W. And then you remember this is the similar step of what we already discussed last time. In principle, this expression is valid for generic X, but the only reason in which is this reliable, in which we care actually, is the one in which we are far away from where the scattering is taking place. So we have to take this asymptotic limit. So the waveform, we only care about it in the regime. The gravitational field is, we only care about it in the regime in which R is going to infinity for fixed retarded time and angles. Now I wanted to make this point because there is some two symbols that mean very different things in the literature, but they have the same letter. So sometimes people use this U to denote this dimensionless combination of the frequency, or sometimes they use it to denote retarded time. I will try to resolve this by using a capital U, although not very important for us. I just wanted to mention, if you read a paper and you find a U, it could mean either of these two, unless you read further. So then the same steps that we applied last time. So last time we were focusing on the soft waveform, but you can look at the notes and find the steps that we did. In particular, there was a sort of expansion by regions in this limit. We find 1 over 4 pi r, basically the same factor we had in the retarded propagator, times e to the minus I omega u, w tilde mu nu. And then what happens is that, you remember, essentially what happens in this limit, if you take this collinear region, is that the momentum of the integrated momentum here becomes collinear to the direction of observation n, except that the frequency stays integrated. So omega n times the well, plus Hermitian conjugate. So conjugate is omega. Yeah. And then finally, reintroducing the factors of 332 pi g. Maybe let me do it there instead of the title. then the formula for H mu nu, the metric calculation becomes 4G over R integral from 0 to infinity d omega over 2 pi W tilde mu nu omega n divided by square root of H by G to the I omega u plus omega. Okay, so now these are just formal manipulations that tell you that in order to have access to your waveform, you have to calculate this W in some way. So that's what we're gonna do. And notice, by the way, that the factor of I that I introduced in the definition of W precisely goes away again in this asymptotic limit, because there was a 1 over I in the saddle point. Okay. Any questions on this? By the way, there are two objects that one could care about. One is really this W is a function of the frequency, which is sometimes called the spectral waveform because it's in frequency domain. And the another one, which is really the signal as a function of time that one would observe at the interferometer, is instead this Fourier transform with respect to the frequency. And in a sense, I mean, they're very interesting. But our next goal is to try to relate these two amplitudes, starting from tree level and then moving up one loop. So our objective is to evaluate this out A out, which is just in 1 minus IPW plus IT in. And of course, A is the annihilation operator that gives 0 when it acts on in, because our in state does not have any gravitons in it. We can just throw away this one. So the leading term, let's say the first term, will just be the one in which we pick A mu nu and then act with the T matrix in the in state. And then we have another term. We do this dangerous operation of pulling out the factor of I. It will be minus I in d dagger A mu nu T in. So then what the exercise that I gave you applies. So these are both operators that satisfy that identity involving the stripping off of the momentum conserving delta function. This is basically the Fourier transform of the function that you get after doing this stripping out operation. So you remember the step is to say label as 1, 2 the integrated momenta in the definition of in 3, 4 the one in out, in order to go back to our picture. And then K, of course, is the momentum of the graviton. So in this term here, you see immediately that what comes out will be precisely the amplitude with 1, 2, and 3, 4 inserted by this in state, and an additional graviton in the final state, which is precisely this pi point amplitude. And then there is minus I. And here, instead, to make sense of this in terms of amplitude, we have to insert a completeness relation. Say here, for instance. Denote it like this: insert 1. And then we see several contributions. The first one comes from the insertion of just 2 particle states, which again, as you can see, will insert a new graviton in the middle of the cut. This contribution will be something like this: just insertion of 2 particle states from the identity, and then an additional graviton that is inserted by this guy over here. And then, of course, there can be higher cut, which we will not really care about today. Let me draw them like this. Okay, we still insert it, but then we could insert more and more complicated states in the middle. This will be negligible at the order which we will stay in the lecture today. Okay. So of course the first the first trivial object that you can build is the one in which you start leading order in G. The leading order of this quantity is order G to the 3 half. And therefore, when you insert it here, you see that 1 power of square root of G goes away. This goes as order G. And then there is a bit of terminology that is not entirely settled in the literature. One could either say that you're looking at the order G waveform because you stripped off this order G prefactor, or at the order G to the second power metric fluctuation. So this is why I mean people usually say 1 p.m. or 2 p.m. when speaking about the waveform, because there is this sort of factor that is not, one is never sure if it's included or not in the counting, but this is what it is. So 3 level. This means sticking to the 3-level waveform in this level amplitude in this wave shape calculation. So yeah, so you remember that this is the I that I stripped off at the very, well, in the previous vector when defining what W is, right? So the bottom line is that W0 mu nu is just the free transform of A0, 5 points of mu nu of Q1 to Q2. And okay, I will not write it down explicitly because it's a bit long. But this 3-level amplitude is known and has been in particular calculated in a paper by O'Connell, Luna, Ridgway, and other collaborators. And then performing its Fourier transform is actually a non-trivial task. In fact, this was this is in a paper by Filippo and collaborators. And the resulting spectral waveform is a relatively complicated object. It's some of these Fourier transforms one can perform exactly. These are associated to diagrams in which there is no nonlinear interaction of the gravity. For instance, this one you can perform it exactly in terms of Bessel functions, K0 and K1, that depend in a sense on this variable u, the dimensionless frequency, but more precisely on omega 1b divided by the velocity, or omega 2b divided by the velocity, something like this. And then there are also additional terms that come from the nonlinearity, which are a bit more complicated because they involve some parametric integrals over these Bessel functions. And then instead the time domain waveform, so if one also performs the additional Fourier transform with respect to the frequency, is actually a bit simpler. In fact, it's been calculated in the late 70s by Kovac and Thorne, and then more recently has been also revisited in a word line formulation of the problem, which is more similar, in fact, to the calculation of the different collaborators, but in the end, it's calculating really the same object. And in that case, the integrals can be performed, and the result reduces to some rational functions times square roots that involve the retarded time of the observer. But I mean, I didn't want to really write it down explicitly. For our purposes today, I wanted just to emphasize that when written down in terms of the barred variable, that knowing myself I will ever is not, they're still there. So when written down in terms of this barred variable, it's 3-level amplitude, so A0 mu nu is so which is just a 3-level block, has the following property when we calculate it in the classical limit that we care about. So if we say that, so you remember all these considerations by now are certain taken for granted, but let me take a step back. We are interested in this amplitude not in full linearity, but in the limit which is relevant for the classical calculation, which is the limit in which the momentum transfers Q1 and Q2 are small of order h bar and much smaller than P1 and P2. And in this kinematic regime, since Q1 plus Q2 plus K must add up to 0, also K scales in the same way as Q1 and Q2. So it's natural to assign a scaling like this, say, let me call it lambda, just as a counting parameter, and the limit lambda going to 0, and then instead P1 and P2 leading order do not scale, so that means they are order lambda to the 0. This is the classical or near forward regime we are interested in. And okay, the statement is that to leading order, this is an object that scales like -2, so lambda to the -2. Let me denote it like this. Plus, okay, if it is really written down in terms of this bar variable, so P1 bar, etc., there is no order 1 over lambda. The remainder is order lambda to the 0. So it's a similar property to what was happening for the 3-level 222. Remember, that was going like 1 over q squared, so 1 over lambda squared in this counting. And then, okay, in that case, it's very simple, just because there is no invariant that you can build the scales like order q or order lambda. It's obvious that the next correction is of order lambda to the 0. There is no here in the middle, there is no 1 over lambda, but the same property is true for this amplitude here, where in principle there are invariants to scale like lambda, right? This omega 1 and omega 2, as you can see, for instance, scale like lambda. But, okay, they have a nice value for this quiz. So now our next goal is to go to the next order, at least formally. Today I'm not writing down many explicit expressions, except perhaps when we are going to getting to the radiated energy angular momentum. Though even there I will be a bit schematic probably. So, so now we are gonna go to one loop level. And then you see that, of course, in order to include all the relevant information at this order, you need to include both the one loop amplitude here instead of just the 3-level one, and then you have to include this additional cut of W1. The Fourier transform of, as you say, A1 once, okay, which, okay, in pictures would be this log with a pole in it, minus, okay. So now let me start by discussing a bit the properties of this thing here. So in fact, I wanted to try to do it in analogy with what we already discussed, I believe, in the second lecture when looking at the next leading order impulse. In a sense, these two calculations are very have several features that are shared, although this one is much more complicated technically. So you remember, in that case, how can I do it? Maybe I can use that part of the blackboard. So in the case of the one loop impulse, we had a 3-level amplitude without this extra graviton multiplied by I q mu, and then its Fourier transform was giving us the q1 pm mu. And then we have managed to recast the calculation as q for the observable as I q mu times the real part of this amplitude plus a cut. In fact, let me try to go back and try to find the expression with the right coefficient each time. Yeah, I q mu real part, and then plus I inside the square parenthesis a cut like this multiplied by a function in that case. And then Fourier transform was so where L is loop momentum, Q1 would be L Q1, and this was giving us Q2pm. So here the situation is similar. What we want to do is to write down this amplitude, not in its, leaving it as a single object, but use unitarity to extract its real part and separate off the imaginary part of the amplitude. So let me give it here. So this is going to be the real part, the one loop amplitude, plus I divided by 2 times the sum over all the unitarity cuts, right? This comes just from the unitarity of the S matrix. And unitarity cuts are all the processes that you can draw by identifying all the possible intermediate states. So, of course, there will be something like this, which you have just a 2-particle state, and then the emission of the graviton is after. Then you have also something which happens in the opposite order. And then now you have additional, so in a sense, these two are very much similar to this cut that we had here, right? They're just 2-particle state, but now, of course, you have 2 possible decorations in a sense. Instead, here, we also have some genuinely new physical processes in which a graviton is emitted and rescatters against either of the massive objects. So these are are sometimes referred to as rescattering or Compton cut, because as you can see, this sub-process here is analogous to what would happen in electromagnetism for Compton scattering, right? Where a photon scatters off an electron. Okay, here is the gravitational analog of that, in which a graviton scatters off a massive particle. So now you see what happens now. If we are inserting this expression back in here, there are two terms that talk to each other, this one and this one. Here you have a minus I and here a plus I over 2. So what happens is that W1 is going to be exactly the same expression, but with this sign flipped. Right? So I can draw it here. So W0, or maybe just 3-level amplitude is giving us W0, or 1 p.m. or 2 p.m. depending on this extra power of. And instead here, okay, real part of the one loop amplitude plus I half minus plus the Compton cut. There we go. And this gives the one loop spectral wave. So now our objective is to try to understand a bit what these beasts do, and following the principle of least action that the physicists love, whether we really need to calculate all of them or not. And and again, I want to sort of, instead of really going through the derivation, to try to draw again the analogy between the two situations. You remember what happened in the case of the 2 p.m. impulse was that in principle, when writing down things in this KMOC language, indeed one needed to calculate both objects in the second line over there, and they both gave a non-trivial order G square contribution, but in the end, the result could be written in a sort of a bit more symmetric form. So the result coming from KMOC would have been something like this. Plus another term, we check mu 1 m squared, and exactly the same result would have been rewritten in terms of slightly nicer variables, but it just takes this form. This is plus order G cube plus order G cube, where okay, be consistent, entirely consistent. Maybe also double check the factor in front of this V check. Yeah, this is correct. Where V check is a combination of V1 check, V2 check. Yeah, the so-called dual velocities, but this is not very important. The physical picture is again related to this drawing that we've been playing with several times now. So the results are equivalent. The two results are equivalent because in the first one, Bj is really the impact parameter orthogonal to the incoming. But here is the vector because I'm not drawing this the time component. These are incoming velocities, incoming momenta. And this is Bj really orthogonal to the incoming momenta, but one can perform a rotation or express the result in some slightly different variables where this is the result. So this would be Bp or B icona, and this we call it P tilde. And this was really reflected in the form of the expression over there, right? So this additional cut was there precisely to capture this additional piece, which only comes due to the rotation from one frame to the other. Okay, what happens in so in other words, what we could have done is that we could have dropped this cut and replaced them and simply evaluated the first one, particularly the 3-level and the 1-loop one, as functions of Be instead of Bj. We note it like this. Drop this and replace B with Bj. Sorry, Bj with B. Okay. So what happens here is that if you go to essentially a similar version of the same calculation that led us to that conclusion in that lecture, sort of a version but on steroids, because of course here you have many more variables and you have to be a bit more careful. But the idea is to play our favorite game, so try to rewrite Fourier transforms of convolutions as product of Fourier transforms. You will find that the same happens here. These two cuts, which are sort of analogous to this one, which have these two particle intermediate states, can be just eliminated. Oops. If you replace, okay, now instead of just Bj with Be, also the velocity. So let me introduce notation to denote this. V1, 2 would be the velocities associated to the incoming particle, and V1 tilde, V2 tilde, or maybe U1 tilde, U2 tilde are the ones associated with the incoming ones. In fact, it's a bit counterintuitive, but the only place where this is important is the 3-level amplitude, right? Because of course this is a difference which is of order G. So it's important that you make the right interpretation in the order G contribution, which then would fit down in the order G squared. So I could also not write it here. But logically, of course, it will also be evaluated there. And now there is an additional sort of twist, which is the following, that you can do this, you can drop these contributions, reinterpret the variables in this sort of more symmetric way, and there is an additional contribution. Let me denote it like this, plus delta tau order G times the 3-level way. So if you neglect this, not only there is this rotation, but there is also a piece proportional to some function which is of order G, which is in fact closely relative to the Shapiro time delay. It's of order G, and then I guess it also has a factor of I and of omega. And so now I want to discuss, we will discuss this in a second. Instead, these two cuts simply remain. They are untouched by this KMOC business, as you can see, in contrast to what was happening, for instance, when calculating the real part of the icon at one loop, right? You remember there, the issue was that there were some cuts similar to these ones in the one loop amplitude. When going to the iconal phase, they will just go away thanks to the exponentiation. Instead, okay, one really calculates the waveform, these are there. So, easy. Just double check. So now we have to discuss still two issues before the driving sort of the derivation to conclusion. The first issue is related to infrared divergences. So in fact, although I just stated that these cuts are physical in the sense that they seem to be there when calculating the waveform according to this KMOC derivation, they have an infrared divergence. And in fact, the goal now would be to try to estimate it, show it explicitly. So let me take one of them, for instance, the one I'm calling it C1 because it's the one of the most practical one in my convention, so the one like this. So of course we can write it down in terms of an explicit phase space integral over the intermediate graviton. And and the idea that of course goes back to Weinberg is that to estimate the infrared divergences of this, in fact, it's enough to look at the limit in this, the region in this integration in which the exchange momentum here, so this can be the exchange of graviton, is very, very soft compared to all the other scales. So in fact, maybe let me try to directly go there. So in this regime, maybe let me also contract with polarization, physical polarizations here. In in this regime, what happens is that in principle, this would be evaluated, of course, at P1, P2, and then the final momentum would depend trivially on the integration. But when focusing on this contribution to the very soft graviton exchanges, what happens is that this amplitude actually factorizes, and the integral is left only on this subpiece here. Leave the intermediate steps here in a bit to you as an exercise. So you factorize out this -2 contribution to the 3-level amplitude, so the leading classical piece, the factor of P1 bar, P bar, P1, P2, times rho sigma, and then you have an integral. So the loop integral is still there, of course. But in this limit, it will be reduced to a two-dimensional integral orthogonal to P1, in the plane orthogonal to P1 and P2. Here is the cutoff I was talking about, and we call it capital lambda minus lambda minus L squared. And then what is left of this Compton amplitude, which is in fact the same amplitude that I gave you, I think, in the second lecture, maybe in the first lecture. We can show you that when we're focusing on a regime which is lambda is very, very small, it just reduces to a factor. So then you see where the infrared divergence comes from, right? It comes from because this is a two-dimensional integral of 1 over L squared, so of course there's an infrared divergence, and you can evaluate it explicitly. So the result is that, let me include a factor of I over 2, of all this cut will appear with a factor I over 2, a unitarity, so I over 2 C1, and okay, and then of course it would be plus pi, right? So this is just a way of estimating the infrared divergence. So I C1, you can have C1, and then you can add also C2 in a similar way. So the one in which particle 2 is the one involving the rescattering, of course. So this is just Ig E omega. You see here, from this would come eventually an M1 omega 1, and then using this identity dimension M1 omega 1 plus M2 omega 2, you can rewrite this as E omega. It's not very important. A0 in this union times minus 1 over epsilon plus log of lambda squared. So we seem to be in trouble, right? Because the physical prediction we get for our observable is divergent, so maybe we have to throw everything away. And the reason why this is not the case is that, as you can see here, this is proportional to the 3-level amplitude. And in fact, so it's proportional to the 3-level amplitude, and this is essentially already known, guaranteed precisely by the discussion due to Weimer, right? We all know that we know that all these infrared divergences must exponentiate. So let me come to this in a second. Maybe since we already have this expression there, we are in a position to play a game similar to a game that we already played, again when discussing the 2-2-2 amplitude, but now at 2 loop. You remember at some point we had calculated a unitarity cut. In that case, it was not this, but it was the unitarity cut associated with the 3-particle cut. We had estimated the infrared divergence coming from this, which also came in minus 1 epsilon plus logarithms. In that case, it was a sigma square minus 1 because it was associated with the invariant S, which is exchanging this channel. And then we said, but if we know that there is such a combination in the imaginary part, by unitarity, this must come from the logarithm of 1 minus sigma square minus I0, and therefore it must contribute to a, so there could be something in front here, of course. This must contribute to something which is I times minus I pi, so pi times the same contribution from. Right, this was this derivation based on unitarity and validity of the radiation reaction at 2 loops in the 2-2-2 amplitude, but of course we can play exactly the same game here. We know that there is a unitarity cut, which is a factor of I in front. It comes with 1 over epsilon and the log. The log, okay, in this case one can show by the actual calculation that the natural variable for each of these cuts is actually either omega 1 or omega 2, so let me call it omega squared. And then the log must come in a factor of minus I pi, so we can predict actually already a piece of the real part, which up to now I haven't said anything about. It's actually, I mean, in a sense, the most complicated part to calculate, but we already know that by this argument there must be a piece in this real part which is precisely pi d e omega by this relation times the three-level amplitude. And this is indeed the only time reversal odd contribution. You remember the reason why we defined this as an addition reaction was the fact that it was odd under v equals to minus v. And the same happens here. The initial reaction contribution to the real part, in the sense that it is the one contributing time reversal odd corrections, in particular to the multipolar waveform, as we will see in a second. So this is a first remark. But then we still have to answer any question on this, because I realize it's a bit convoluted somehow to explain it. Easier to do than to say. So, easy prediction on real part of this beast. And then, of course, there is much more inside the real part of that. It's just not going to be time reversal on. So, what we still need to discuss is what to do with this infrared divergence. But I sort of already hinted at what is going to save us. So, the key idea is to realize that both this infrared divergent piece and in fact also this sort of unexpected or slightly unwanted piece are of the form I omega times the three-level amplitude times something. And now we have to remember the very first step that we mentioned, that what we are actually interested in a sense, is not really just this W tilde, but it is Fourier transform, right? I minus I omega u. So, and then there is the integral. Let me just focus on this combination. So what we can do is that we can shift u goes to the u plus g plus times a function, right? So redefine the origin of retarded time is a u independent function. And then what happens is that this is going to go to, say, let me write it down, w0 plus w1 times, okay, the expansion, this is order g, we can expand it out, 1 plus I omega or minus I omega gf. Right? So then, expanding order by order in G, we see that effectively we have transformed W0 plus W1 into W0 plus W1 minus I omega GF W0. Or if you want, you can run this backwards. You can first exponentiate these sort of dangerous or unwanted pieces and then hide them away or renormalize them in a sense, right? By redefining the origin of retarded time. So this is in fact the way in which we can remove this 1 over epsilon. And if we want to, at this point, since we are allowed to do translations by an infinite amount, 1 over epsilon, which physically just means dropping the interpretation of this calculation as being able to predict the time of arrival of our waveform. So we can just say we have to wait as experimentalists, and then at some point there will be a waveform, we don't know when. But when it starts, we can fix our origin of retarded time experimentally, and then the rest is going to be fixed. So in particular, the wave shape, the dependence on u is going to be fixed. But to write down an expression, it's completely irrelevant how we fix the origin of retarded time. So besides this 1 over epsilon, of course, we can perform shifts of finite order. So whatever, I mean, for instance, we can remove this piece. And a way of remembering that there is this ambiguity is to remember that, okay, by dimensional analysis, here there must be an fixed scale, right? This mu, which is nothing but another finite shift. So let me write down something, renormalize retarded time, or the origin retarded. In fact, this was already discussed away from this amplitude context in papers in the PN setup, in particular Ross, Porter, Ross. Okay, so after all this, let me write down what is left in order to have a clean picture of what is left after all of this. Maybe one comment, which is important, in fact, it played a role in recent comparisons and of course can create confusion, is that when we say that we subtract this object, we really mean that we subtract 1 over epsilon times the d-dimensional 3-level amplitude. If we work in Top-Veltman regularization, so this is d equal 4 minus epsilon dimensional. And the key point is that this must be consistent with the prescription that you use to calculate the amplitude, right? If you calculate the amplitude in conventional dimensional regularization, in Top-Veltman regularization, you should do the same here. And here it's important because, of course, there is 1 over epsilon times the d equal 4 contribution of this, which is divergent. And then we worry about that and we subtract it. But then there is a finite piece that comes from the order epsilon part of this A0, which multiplies the 1 over epsilon and then gives a finite piece, which, by the way, is not proportional to the 3-level amplitude in 4 dimension, right? Because it's proportional to Taylor expansion around 4 dimension. So this is, leaving it will not be a further redefinition of retarded time, it will just be a mistake. So it's important to subtract it, be consistent. And then the only scheme dependence or ambiguity is this additional finite shift in U. So let me tell you what remains. So W, including 3-level and 1 loop, is given by, okay, the real part, let me remove the theta stay in momentum space maybe. By the real part of the 5-point amplitude plus in order to highlight this, let me define a regulated Compton cut, which is the Compton cut minus these contributions that we can separate out from here. So plus I cut C1 reg plus, okay, these logs that I put down, 1 omega 1 log omega 1 squared divided by mu squared, this complete scale. Okay. And then let me see where I could erase. Okay, let me erase the 222k for an additional piece of information I wanted to convey. So now we understand a bit better this Compton. Okay, very explicitly this the separation. Let me define because as I said it can be a tricky point. So C mu nu would be the complete Compton cut as I drew it there. And then what we are doing is stripping out this 2IG and 1 omega 1 minus 1 over 2 epsilon plus the log on the omega 1 represented by mu times the 3-level amplitude in the dimension. As I said, this is important because of this. Plus I over 2 C reg mu and similarly. Okay. Now before going to the break, 2 additional points. The first point is that you recall there was a piece which of this real part which was actually easy and proportional to the 3-level amplitude. So we could we call the full real part we call it B or B1 since we are at 1 loop. Then B1 can be broken down into 2 pieces: B1 odd and B1 even. B1 even is the actually complicated part or truly 1 loop in a sense. And it's called even because it's even under omega 1, omega 2 goes to minus 1 omega 1. And then B1 odd is actually can be further broken down into B1 odd, let me say integer, and B1 odd half integer or radiation reaction. So this is the radiation reaction part that we talked about here, and the expression is 2 minus 3 I think it equals a minus plus 1 pi d omega, the 3-level amplitude. I'm going to double check the factor. So this is, as you can see from here, as promised, this is these two have different scaling with the velocity, right? Because remember, the velocity is basically square root of sigma square minus 1. So this is, in particular, from here it would seem odd, but actually when you multiply by this, it's even in the velocity. And this is the odd piece in the velocity given by the initial reaction from the contact. This was the first remark. The second remark is that okay, today we have been focusing on the dynamical part of the waveform, so really for frequency bigger than 0, right? And you remember last time we had a discussion that in principle the static part of the waveform can be affected by super translations, and there were two interesting frames. One in which the asymptotic shear goes to 0 in the far past, and one in which the asymptotic shear in the far past is dictated by particle 1 and particle 2. So here in the discussion today, implicitly we've been working in case in which there are no static modes, nothing. So the shear goes to 0 in the far past, and we are in the canonical frame. But now one could wonder what happens when you go to the other frame, the intrinsic one. So you remember we had to perform a super translation to go from one to the other. We'll write it down in a second. But maybe first let me give you the punchline. So of course this will generate a static piece, which is proportional to a delta function of omega. So it doesn't really talk to anything that I wrote down today. But then it generates an additional piece because remember the super translation function has two pieces. Let me write it down again. This. Oh. BMS frame. So we are in the canonical frame in which the shear goes to 0 in the far past. But now we want to move back to the so-called intrinsic frame, where now shear is dictated by the incoming particles here and by the outgoing particles there, plus corrections, of course. So to do that, we have to undo. Well, last time I actually discussed the opposite. So in a sense, you have to, if you check your notes, you have to undo the transformation that you wrote down a few times ago. Well, last time, I think. In T, function of the angles given by 2G, sum over the incoming particles, dA dot n log of dA dot n divided by a constant, which we could say is the mass. So you see what I'm trying to say is that, of course, performing this transformation will induce a piece, this guy here, which does not depend on time. CAV is the TT waveform, so it's really this W we are calculating, and projected over the physical polarization orthogonal to the tangential to the sphere. So this will be a time-independent piece, which translates to a delta function contributions in a frequency domain. Say we don't care about that. Then we have to care about this guy over here, which, as you can see, is proportional to t, does not depend on angle, but then has a derivative with respect to the waveform, which does depend on time in general, and in particular as an extra power of g. So in order to calculate the effect of the super translation at leading order, so on the 3-level amplitude, we don't care about this piece because it's going to be proportional to an additional power of g. But when we go to the next leading order, in particular here, we have to care about this piece. And in particular, it's going to be something proportional to the Fourier transform of du, so I omega, times the 3-level amplitude. And then there is going to be some dependence on the angles. Okay, you can check that the net effect of this is to multiply this factor by 2. So, of course, there is an additional piece that is just omega log omega, and this doesn't change, but this we care about the dependence on the angle. When you remove these omegas, this is the piece we transform by going from this intrinsic and BMS frame. Okay, so this is more or less what I wanted to say in the first lecture. Any question? Okay, let me put a fudge factor here, depending on whether you want to stay in one frame or the other. Now, in order to rephrase what we already said last time, it's not entirely clear what if the super transitions have physical meaning. In fact, it would require, from an experimental point of view, just looking at the waveform, you would need to be able to check the angular dependence, the time dependence at different angles with respect to a single source, right? Because this is a angle-dependent time translation, so you would need to check that the signal for an observer sitting at a different angular separation is a bit delayed or advanced compared to your own. And this is practically not possible because the sources are just too far away and we just see them coming as a plain wavefront. We don't have enough resolution to resolve different, we cannot go far enough in order to resolve different angles. So practically, it just means that what is really observable in this complicated expression is the time signal at a given angle as a function of time. But, okay, this is okay, so maybe you can take a minute break. No questions?
Okay, so break for 10 minutes.
the last effort. So maybe let me start by making something slightly, a point slightly more precise. Of course, what changes is not really the coefficient in front of here. Here, first you should strip off the part which is just proportional to log omega and log omega. So strip out an overall scale from there, and then the super translation in the given frame only changes the dependence really on the angles here. So what I was calling P1.n, not P1.k divided by the mass. So the overall scale in the given frame does not change under super translation. The other remark is okay. To emphasize once again a point that we already know we're talking about the radiation reaction at two loops in the 2 amplitude, but here it's being analogous. And the remark is that the amplitude is a bit complicated, but it can be broken down in a natural way in two pieces, which have different behaviors under velocity going to minus velocity. So let me try to make this point a bit more precise. So we already remarked that there is a piece in the real part, the radiation reaction piece, which I said is odd under velocity. Let me try to explain this a bit better. And together with this, the only other contributions that are odd in this sense come from these guys here. So the Compton cut, the regulated Compton cut. And okay, possibly this super translation dependent shift. So these pieces highlighted in red are odd in velocity in what sense? So it's not just that when you expand them in the Taylor series, you just find even or odd powers in velocity. It's a bit more complicated than that. The idea is that the waveform can be decomposed into in a given frame. The traceless measure can be decomposed in multiple. So these are a generalized version of spherical harmonics that we don't go much into details, but they are a function in L. That's a coefficient that now I forget, but they have the decomposition in terms of this kind, where Ni are the components of N, our direction unit vector, and then there is also a combination involving V. There are two different multiple with slightly different behaviors and different behavior under phi, so the electric and magnetic multiple. Now the statement is that each multiple only receives corrections that are even in the velocity or odd in the velocity, depend on the ingredient that you look at. For instance, if you look at this guy over here, this will only generate even corrections in the velocity to each multiple. Similarly, if you look at this B1E, maybe let me use a different color to highlight the even part. So the even part will be this one, and he said the other one, so the one coming from the initial reaction, so this one, and the one coming from the regulated Compton cut, give instead odd correction in the velocity to each multiple. So this is of course, even and odd is with respect to the leading one, which is the Einstein quadrupole, which we all know and love. Okay, but just so point, I mean, being faithful to the rest of the spirit of the spirit of the rest of the course, at least once we are gonna want to play with our favorite trick, which is to rewrite Fourier transforms of convolutions as products of Fourier transforms. One can try to play it in different radiative observers. One attempt could be to do this regulated cut. One I will discuss in some detail is the application to the calculation of radiated energy and angular momentum. We're going to stay at order GQ, the leading order at which these receive contributors. So the idea, so let me start by recording some general formulas. It's convenient to rewrite everything in terms of this W, which by the way satisfies the word identity. Exactly. You remember, in contrast, what happened to the static portion of the field, which also has some longitudinal components, which was a bit trickier, but today we can work with this. And then one can adopt two sort of different or complementary approaches. One is to start again from KMOC, and for instance, if one is interested in the energy or energy momentum, insert the energy momentum in the sandwich that is dictated by the amplitude approach, and similarly for the angular momentum. Another approach which leads to the same result, and maybe for us today is a bit easier, is to recall that people have worked on this before us, and we actually know the expression of the energy and related angular momentum in terms of the waveform. It's just that people usually express it in terms of the TT waveform, that we call it lowercase w, is the TT projection of our capital W instead. And okay, let me maybe once spell out this TT projection in detail. So we are decomposing our K as omega times n, and n itself in a given frame is we decompose in this way, with n being sin theta cos p, sin theta sin p, cos theta. And then we can choose this reference vector that appears in the definition of phi, for instance, in this way. 1 minus n, because in this way satisfies lambda dot n is equal to -1. And then the TT projector, sorry, the transverse projector, which is just theta plus lambda becomes this purely spatial matrix, just literally the projection orthogonal to the spatial projection orthogonal to the direction of n. And then, in terms of this little w, for instance, the total energy momentum is radiated by the system is given by this formula. This is the same formula that last time we derived from amplitude, although of course they are incompatible. Otherwise, it means there's something wrong. Basically, the square of the waveform times the momentum of the graviton integrated over the free space of the graviton. It's essentially exactly what you imagine it should be. And now, okay, the usual step that we also did last time, but we recall, is that when we replace when we replace little omega with capital omega, we have in principle these pi's in between, but since capital W satisfies the word identity, these terms in the projector simply drop, and one is left with the, oh, by the way, of course, there is the version for the graviton, which I didn't write down. And then we're only left with the usual structure. And then here we apply our usual trick. So this is the product of two Fourier transforms, which are very complicated in frequency domain. And the idea is that it's nicer if we go back. So the usual the steps is really the same that we did for instance, when doing the imaginary part of the 2 to 2 amplitude. Simply we did not have this k. Just let me recall the basic idea is that at some point you will have some delta of p1 dot q1, and somewhere else a delta of 2 p1 dot q1 prime plus q1 plus something else. And the key step that you have to remember to do is that you can just neglect this piece thanks to the other delta function, and this allows you to rewrite. And I'm not giving details because I want to do this, if I have time, I want to do this in more detail for the angular momentum where there is an additional subtlety. So then you can rewrite this as the Fourier transform of the integral, now about 2-loop integral of the convolution of the 2 to 3 amplitude to this leading order, right? So at LO in the coupling times K, well, this is let me write this to emphasize this is a 2-loop integral. So now let me come to the more interesting case of the angular momentum instead. Basically how I wanted to end the course. So for the case of the angular momentum, the situation is slightly more involved just because we have derivatives, of course, right? So the standard expression will be the J, the radiated J. Let me break it down in a given frame as an angular momentum due to the orbital part and to the spin part. The orbital part is minus I integral over K W mu mu tilde star K alpha d K beta W minus, okay, these two contributions actually integrate by parts of the same object, but I don't know why in my notes I show them like this and copying my notes. Mu mu star. And then there is the spin part, which is minus I integral, okay. Twice, this 2 is due to the spin of the graviton, basically. Star mu alpha mu beta. Like this. Okay, so the first simplification would be if we manage to rewrite in use of the capital W instead of the lowercase w, because then we get rid of the dependence on this additional vector lambda, which, as you can see, is not particularly nice in general. And it's also, I mean, depends on the frame in which you are performing this. So this step, this can be done. It's just a bit more complicated because you have to let the derivatives also act on pi. In fact, some time yet, so I think I should make it. I wanted to do a similar exercise, but for the photon, because it's on the blackboard, it's a bit easier. So let me try to do that. So for the photon, the step would be similar. Let me call it. And then essentially the other one is left to you as an exercise. There will be little f instead of little w. Let me simplify a bit the notation just to make things slightly quicker, hopefully. And f is now capital F except for the transverse projector. And d is a shorthand for this k alpha d k beta. Okay. So now the key properties that you need are the fact that that F, now capital F satisfies the word identity. Exactly. So let's see how we go. So to begin with, little f is capital F minus, plus lambda mu k dot f plus lambda k mu lambda dot f. If I apply just the definition of transverse projector, but this is 0 by the word identity, right? So we can just work with this term and this other term. So let me start from the first piece. So f star mu d alpha beta f mu, which therefore is going to be star mu d alpha beta capital F mu plus just one term k mu lambda dot capital F. So the first term, okay, we just act, the operator will just act in here. And then here in principle, it could act either here or here. But you see that if it doesn't act on k, k will contract with little f, which is transverse, and that will give 0. So we only need the term in which d acts on k. So calculate it here. This is the result, right? Because this is just the derivative with respect to k beta or k mu, which is the delta. So all in all, we have capital F star mu plus k mu lambda dot f star, where I just expanded the definition of f star, derivative of f mu plus f star mu, which is contracted with this delta now, so k alpha, bring it in front, lambda dot f will be later, and then f star beta, lambda dot lambda dot f. And then, okay, the first term is already looking good, star mu d alpha beta f mu. And then here, this term we can try to sort of derive by parts, right? Because again, if k mu contracts f, it's 0 by the word identity. So then we can integrate by parts the derivative. So we can rewrite this as the derivative acting on f dot kappa with f dot k, which is 0, minus f mu times the, so this is going to be, maybe let me write it down, minus lambda dot f star f mu d alpha beta k mu, right? Plus k alpha star beta lambda dot f. And here we use the same identity as before to conclude that this is equal to f star mu d alpha beta f mu minus lambda dot f star k alpha f beta plus lambda dot f k alpha f star beta, which you could have guessed because the thing must be imaginary. And spin term is simpler. That means I need f star alpha f beta. So let's start by, well, let me decompose both of them. So f alpha plus k alpha lambda dot f, f beta plus k beta lambda dot f minus alpha beta interchange. And so you see that there are in principle 4 terms, but one of them will have the antisymmetrization of k alpha k beta, which is 0. Then you have f star alpha f beta plus k alpha antisymmetrized f beta lambda dot f star plus k beta, or maybe let me write it afterwards, lambda dot f star k f star alpha k beta lambda dot f plus 0. And now, if I didn't make a mistake, here it should have been capital alpha, capital F all the way. Apologies for that. So now, this term and this term have the same sign, but they have alpha and beta interchange, right? So they cancel against each other. And the two terms instead are exactly opposite, just manifested because they have the same. So the result is that if a capital F satisfies the word identity exactly, then ij alpha beta is equal to the integral over k f star mu d alpha beta plus f star alpha fb. Which is yeah, formula, and the similar one for the gravitational equilibrium exercise appeared first, I think, in a paper by Manuel, Ridgway, and Shen. And then in our papers by Paolo and Rodolfo. Okay, so then this is a first simplification. So let me give you the formula for the graviton, at least the one which I leave to you. I mean, the derivation is exactly the same. It's just that it involves more terms, and also the trace part is around. So the result is the following: so J alpha beta. Now end the total part is minus I over K. Our favorite structure, lambda mu rho eta mu sigma minus 1 over d minus 2 eta mu eta rho sigma w star mu k alpha d w rho sigma di k beta plus mu w star mu alpha w beta mu. There we go. So the first step, so eliminating the dependence on the reference vector, works. And now we have the second step, which is to rewrite this as the Fourier transform of a three-particle convolution. This is slightly trickier, again, because of the presence of these derivatives. So let me try to show how one can work it out. Of course, instead, this term is exactly the same as the one we discussed before, right? Because this is just a product. It's just that the contraction of the indices is slightly different, but there the exercise is exactly the same as the previous time. So the only non-trivial bit is that one. So let me call this like JO and this like JS. Although, as you can see manifestly from this derivation, the distinction between the spin term and the angular orbital part is no longer meaningful, right? Once you rewrite these things in terms of the capital F or in terms of the capital W, because there are this non-trivial cancellation between the two terms. So now what I'm calling O and S are reminiscent of what their grandfather and was, but not exactly the same. So only the sum of the two is meaningful. This is minus I use this shortening notation alpha b, d alpha beta. And then there will be, okay, there is this convention we are using throughout. That if no indices are shown, means that they are contracted with this structure here, as usual. So then we have the two Fourier transforms, one here and one there. And I choose to solve the Fourier transform. Remember there would be the integration over Q1 and Q2, but Q2 can be solved in terms of Q1 and K. So that's what I choose to do. B1 dot Q1 W 1K. And then I choose also to work in a frame where B2 is equal to 0. So if you prefer, particle 2 is initially in the origin of the transverse plane. Of course, this can be undone at the end because we know how these things transform under translations, and then we can simply perform a translation to put it back to wherever we want it to be, times the other two transforms. So Q1, and then we have the Q1 prime, let me call it. In the minus I B1 dot Q1 prime W. So this is in full glory. And okay, so with the idea that here the derivative only acts on the first row, right? This is a derivative with respect to k, and it will act in particular both on this delta function and on the amplitude. So the tricky bit is the one in which it acts on the delta function, because there we can no longer use our favorite trick. The product of the two delta function can be massaged, right? So the idea was to use the fact that delta of x times delta of x plus y is equal to delta of x times delta of y. Right? But the problem is that now there is a term in which there is no delta, there is a delta prime. So that's what we need to think about. More precisely, what we have is, well, not, let me not write everything, otherwise it would take ages. So what comes out of here is a term in which you have d alpha beta acting on w. And this is fine, right? Because then you can exactly play this game because derivatives don't act on the delta function. So okay. And then the tricky step I was hinting at is the one in which the derivative acts on the delta function, and then in that case you get delta prime 2p2 dot q1 plus k 2p2 alpha k beta, or beta k alpha. K alpha. Okay. And now the key trick is to use a general, I mean, a different version of this identity that does involve delta prime. So in particular, the issue will be when we shift the integration in order to reconstruct the overall delta function. These two will work in exactly the same way as before using this identity. And these two instead, this will talk to this one, and we can use the following result, which you can prove by integrating against a delta function. Minus 1, for instance. Delta of x, delta prime of 1. So basically, in a sense, you can pretend that this works, this term, right? You can just set x to 0 in this term, but then there is a price to pay, which is you pick up another term. So using this identity, you can actually go through. The problem is that you will not just have the naive bit. So eventually what you can do is to write this as the integral minus I integral of k of, let me call it the naive piece, in which you let the derivative act on everything. So pdk alpha beta, and then okay, and then I pulled out the Fourier transform. So now here I want to put the three particle cut exactly as we did before, including its measure. Let me make it explicit. The Lorentz invariant phase space measure, which depends on Q1 and cap and K. Of course, I need to break this down because the derivative only acts on one of the two 5-point amplitudes. Oh. Okay, so in which the derivative acts both on the amplitude like so, and on the phase space measures. And then you take the Fourier transform at the very end. But then this additional piece spawns the following term, plus I u2, so the velocity of particle 2, times a derivative with respect to the longitudinal component of the momentum transfer, the same phase space integral, but now without any derivative. So this is where this delta prime has played a role. Okay, let me make it even more explicit. So this is Q1 minus Q, for instance, and this is cap. Okay. KB times now the three particle cap, the usual one. Okay. So alpha beta, all these is simply there. So this is the final formula that we can use. The only subtlety is the following: that okay, the first one is really the naive piece that you would simply guess by carrying this derivative through and forgetting about this issue of the delta functions that are not exactly on. There are some delta functions. You don't care. You just act with the derivative on everything that depends on k. And the second term is, you see, basically this is exactly the same integrand that we had for the radiated moment, energy momentum, right? It's k multiplied by the three particle convolution integrated over free space, but there is a derivative of q parallel to, what is this guy? So q in the Fourier transform, sorry, then there is the Fourier transform somewhere. In the Fourier transform, you remember, this is the one performed with respect to, there is a delta p1 dot q, delta p2 dot q. So q should be orthogonal to p2. Instead, here what you should do when you glue these two amplitudes to construct this three-particle cut is not to assume these kinematics already. You have to glue them by keeping the component of Q2 parallel to Q2 in particular. In general, Q can be decomposed this way. And normally we would only keep this guy, right? Because this component and this component are killed by this delta function. For instance, here, this is what you can do because the Fourier transform acts directly on this glued amplitude. Instead, here you have to be a bit more careful. You have to first glue the two amplitudes by keeping these two generic. Actually, Q1 you can directly for Q parallel 1 you can directly forget. Instead, Q2 you have to keep it, then take the derivative, and then set it to 0 after taking it. So this is the only slight commotion that happens. But otherwise, the derivation goes through. I mean, the calculation in the end is exactly the same. It has particularly it has the same time of the integral and so on. Okay, so this is the trick that works. This is last time we're gonna it's going. And so maybe let me state the result for this leading order, so or the G cube energy and angular momentum. So these are this can be written down, pulling out some factors by dimensional analysis, essentially the cube, and then there's a function. Please you check. Sorry, I'm alternating a bit between u and v for the velocity of the particle, but at this order it doesn't matter. All this one. And then also beta. B. And then I'm going to factor it with calligraphic F. B alpha u1 tech beta minus B alpha u2 tech beta. So this does not depend on the reference frame for translation, and these are covariant vector under boost and rotations. This guy instead is also a tensor under boost and rotation, but it depends on the translation frame. This is written down in the frame in which B1 is equal to minus B2 and equal to both equal to an absolute value to B over 2, which is nice because it's a frame in which the 1-2 symmetry is manifest, as you can see from here. These two go into one another because you have to remember that, okay, U1 goes into U2 and vice versa, and B changes sign because B is the difference between B1 and B2. And then this function is F, let me write it down in great detail, but they are, for example, epsilon was given, being first in a paper by Julio Martinez, Enrico Herman, Michael Rufer, Mao Zeng, and they are polynomials or polynomials divided by sigma square minus 1 over 3 half plus another polynomial divided by square root sigma square minus 1 times log of sigma plus 1 and f3 away square root again 3 half, no 5 half times arc cos sigma. And a similar structure for f with of course different polynomials here. And they can be obtained by reducing these loop integrals and evaluating loop integrals. And then this kind of pipeline is nice because it can be generalized in an easy way to different amplitudes. So this is the result for minimally coupled massive scalars, which is the first trivial example you can think of. But then you can, if you add the appropriate ingredients to these 5-point amplitude, you can construct generalizations. For instance, you can include the tidal effects, and this has been done also in works by Filippo, and for the energy momentum, and I did it for the angular momentum, is similarly for the spin, for instance, you can include. So it's rather flexible. The idea is that if you know the building blocks, you can apply the same machinery to generalize the calculation in different directions. So maybe to conclude, let me remind you of a puzzle that already appeared last time, but then we solved it, but now it has reappeared in a different form. And the puzzle is the following. So here, puzzle. So you remember at some point we were complaining that the total energy emitted by the soft gravity seemed to diverge, but then we managed to calculate it in a different way, which was non-perturbative, and in that case we simply realized it was non-analytic in the coupling. So here a similar situation is present. It's still open. So if you divide by the total energy, the center of mass energy that is radiated, so basically P0 or P0 rad, this guy over here, literally the time component in the center of mass frame, and you take the high energy limit of that, you will see that this case like theta 1 PM cube, which is good because we expect theta cube because it's dq, and theta 1 can be kept, theta 1 PM can be kept fixed and small, also in the high energy limit, but then there is square root of sigma. So this seems to say that if you trust this formula, you will be able to radiate much more than the total energy that is already initially present in the system, which means that the prediction is nonsensical. And it's speculated that the same mechanism could work in order to generalize for energy, but this is still not known. And I mean, you can be content to say that probably this is indicating again simply a breakdown of the predictability of our PM regime, because we are going beyond the so-called the bound that we saw also last time, right? The PM bound on the validity of the PM approximation in general is that sigma can be large, but not as large as 1 over theta 1 PM squared. And if you stay in this regime, indeed you do not radiate a nonsensical amount of energy, but it would be nice to understand what happens beyond this. Okay, so since we are really at the very end, and I have any questions? Yeah.
I didn't really understand the last remark you made. To say if we stay in PM limit, I mean in PM regime, which is where we are doing the calculation, there is no puzzle, but then what is left to be understood? I didn't get.
Yeah. So let me do a more historical set. So in a naive way, you think that the PM expansion is an approximation valid for small g over b and generic velocities. Okay. Then you look at this object, which you can keep g over b fixed, but for generic velocities it becomes very, very large. So it means that there is something wrong. Then by studying other examples, you realize that in more controlled examples, velocities can be large, but not larger than this bound, in order for the predictability of the PM expansion to be true. So then you could say, okay, there is no puzzle because we just trust this, first of all, for generic but not excessively large velocities. So this is true. Of course, you would still like to know what happens beyond this bound. This is still not known. For instance, in this limit, you would in principle should be able to match, if you manage to do things properly, the regime in which the two objects become massless.
You have a question?
Yeah, Panagiotis, I think, has a question, please.
Yeah, hello. Sorry, I wanted to ask exactly what you are saying now, actually. But I mean, if I was, my question is like, which exactly had been the regime, if it's not the PM, in order to access this high energy limit?
Yeah, it's a regime in which the velocity is very high. Deflections are still small in the sense that theta 1 PM, so GE over B is small. But velocity can be arbitrarily high, in principle also ultra relativistic or massless, velocity of light in the case of massless particles. For instance, the scattering of two shock waves which have sufficiently large impact parameter to have, so let me spell it out explicitly, GE over B fixed and small. You can always do this, right? Because for very large E, you can still go to very large B in such a way that this parameter is fixed and small. But then at the same time, you can, sigma can be arbitrary, right? You have two parameters we should play. So this is the regime which is still not understood. There are works by Veneziano, Ciappelloni, Colferai, and other collaborators in which they try to analyze in particular the spectrum. So you see in particular the problem is that this divergence seems to come in the spectrum d omega by the fact that the very large omega, this thing seems to go like 1 over omega, and therefore it's logarithmically divergent. So then in the paper they say maybe there should be a cutoff at some point in which the behavior is even more suppressed, and then this is the regime. So for very large, sorry, this would be ERAD, so dp0 if you want. For very large center of mass energies, this can be the behavior, and it's still not exactly clear. That's why I'm mentioning it at the end of the course, because the food for thought.
Sorry, can I ask another thing?
Sure.
I just correct me if I'm wrong, but does this mean that that this is not a calculable thing because of the starting assumptions of the PM expansion? Like this, the Goldilocks inequalities, is the problem coming from the starting place, or is it just we don't know?
Well, in a sense, it is non-calculable because you are bounded by this inequality. So, yeah, if you are happy with saying I only work in the perturbative PM approximations in which I can trust the perturbative series in powers of G, then your point of view is simply I don't care because this is beyond the regime I'm interested in.
Thanks.
Yeah, so maybe this is the very end. Let me conclude with a few words about the perspectives, etc. So, so in these lectures, we try to provide an overview of some of the recent development in this connection between amplitudes, the gravity, and position for gravitational wave observables. So just to sort of reiterate or review, we covered the impulse, 11 and 1 loop. We hinted at some features of the impulse at two loops, in particular this radiation reaction. And then we moved to discuss a bit the Eikonal exponentiation, the Eikonal operator, a little bit, at least in the soft limit. In fact, there is a version of this Eikonal operator that captures also this non-zero frequency or beyond soft waveform, although I didn't touch upon it in the lectures in detail. We have discussed the connection between the soft theorems in the amplitude perspective and classical soft theorems from the waveform, in particular the memory effect. Also there are interesting developments because in these lectures I focused on the memory effect, which in frequency domain is really 1 over omega pole in this W. But then there are corrections to that. In particular, Sausan and collaborators have shown that there are other universal predictions under log omega, log omega squared, and in fact last year we and also another paper proposed a generalization of this that resums things in terms of something of this form. Some function here. So the idea is that all these logs are supposed to be universal and simple for the two-to-2 process. And then we discussed a bit relation between these soft theorems and BMS symmetry, and also beyond soft, the fact that this today we discussed the fact that this BMS translation also affects non-soft part of the waveform via this homogeneous term, right? The one that changed the factor of 2 we mentioned at some point in the dynamical waveform. And then, especially today, we concluded by flashing or reviewing a bit the derivation of the waveform from amplitude, that 3 level and 1 loop, and the derivation of radiated energy momentum and angular momentum. So maybe to conclude, let me mention a list of things that we did not cover. Here, for instance. By now, of course, the literature is vast, and clearly 5 lectures were not enough to cover all of it, and also my expertise is limited. So we did not include a detailed discussion of the impulse at the 3 loops. So order G to the 4. This has been achieved, in fact, in complete generality already by different groups, so the result is stable. There is a vast literature on the inclusion of spin effect. And I would add more generally on considering things that go beyond this point particle minimal coupling approximation that we consider here, including time, including different gravity theories, modified gravity, including scalar hair, including several types of effects. The idea that this sort of framework is relatively flexible. So the objective, if you want to extend what we did, is to modify the building blocks that we employed in our derivations here and there, but essentially the spirit of the calculation and also the technical steps after that are very similar. And in all these lectures, we focused on what happens to our beloved two-body scattering process, but of course, experiments care more about bound systems for good reasons, although today, with the growing body of data that is being accumulated, also collaborations are starting to look for more exotic types of systems, including possibly so-called captures or scattering. So let's see what happens in the future. But there are also techniques to export what we did to the case of bound systems. And this in particular goes under the name of boundary-to-bound correspondence in the papers of Rafael Porto, Gregor Kalin, and other collaborators. And so export, for instance, calculation about the deflection angle in one case could be analytically continuous to the calculation of precession angle in the other one, and more refined statements can be also made. And then, especially recently, an interesting and promising direction is to try to join forces with other approaches. In particular, the idea is to combine the Pn expansion with insights that come from the self-force expansion. So in the limit in which one of the two objects is much lighter than the other one, gives another organizing principle either for simplifying PM calculation or for trying to resum them. For instance, the case of this higher order soft theorem was precisely due to the comparison between different approaches, in particular with Pn and with the self-force. And then, things that are a bit at the boundary of what is currently known. As I mentioned, people are working very hard on the order G to the 5, again using insights from self-force to break down the calculation impulse. And then I discussed a bit the radiated angular momentum at order G cube, and the order G to the 4 are known for the impulse, not completely yet for the angular momentum. And then perhaps the last thing I want to end with is again to remind of this high energy puzzle, which is of course not very interesting from the practical point of view or experimental point of view, but it's conceptually a nice challenge which lies ahead. So with this, I thank you for your attention.
Maybe other question? Last chance.
Comment, complaint, feedback. Yeah. Panayotis?
Yeah. Yes. Thanks for the lectures also, Carlo. Okay, one last question that I have is Again, can you please, because I think I didn't get that from the lectures. There was a problem with the angular momentum, the radiated angular momentum, at which order it starts.
Yeah, I mean,
For some,
I can invite Filippo to. Yeah, so the issue is the following. Whereas, so let me stick to the sort of amplitude-based perspective that we took. In the calculation that we sketched today, in which you're really calculating this integral over W, possibly with an operator W star. What changes when going from the angular momentum to the radiated energy momentum is that you change a little bit what you put here inside. In one case, you would put K alpha, and in the other case, you would put this slightly more complicated operator with derivatives and anti-symmetrization on the indices. But clearly, the power counting in G doesn't change, right? Because to leading order, this waveform is just a 3-level amplitude for the 2 to 3 process, something like this. And this clearly goes in order to G to the 3 half. So this object is going to go to order G, the cube, or the G cube. Now, instead, calculations done, for instance, by Thibaut Damour, but also by other people in the PN context, for the angular momentum, find a result that is already order G squared. Now, the resolution of this apparent puzzle is the fact that this contribution is really the one due to dynamically propagating gravitons, because here we put the non-zero frequency waveform, particularly the one that satisfies the word identity, so really does not have any longitudinal mode, and this is the result for the radiated energy momentum and radiated angular momentum in the strict sense of the word. So because there is carried away by radiation. Instead, another G square contribution comes also in the results we discussed in this lecture from the static field. So in particular, if you want, it's a contribution that is due to the fact that the system loses some angular momentum also by interacting with the static gravitational field. And this is due to this I epsilon part in the F mu nu that we saw last time. So in the end, there is no, in a sense, there is no paradox because you're calculating two different things. And in one case, you're including the angular momentum that is lost due to the interaction with the static, so non-propagating gravitational field, and in the other one, you're not. And this one starts at order G squared. Let me add maybe that, of course, maybe the fact that this is static means that in frequency domain is localized at omega equal to 0, but any reasonable detector has a frequency band which does not include omega 0 equal to 0, in around the hertz, tens of hertz, for instance. So in a sense, this is not really observable by looking at the waveform because we don't have access to the infinite time observation. What one can hope to measure, and as a consequence of the dynamics of the binary, is the total loss of angular momentum by the mechanical system. So the balance law, if you want, right? And this was discussed also in great detail in a paper by Filippo and collaborators. And essentially, the bottom line is that in order to have an object, let me call it boldface J plus calligraphic J, meaning the radiative order G cube plus higher and the static, which represent, if you want, minus the variation of the mechanical angular momentum of the total system, you have to include both. So in a sense, maybe for practical purposes, the interesting thing is to actually calculate the sum precisely because, I mean, our interferometer experiment will just measure the radiative angular momentum, and or by observation we could hope to measure the change in mechanical angular momentum. Then there is a whole story related to the BMS invariance or not of this observable, but maybe for the last 5 minutes of the last lecture, this is not the appropriate time. But yeah,
okay,
I would refer you for, maybe to the paper of Filippo, Massimiliano, and Wong, I think.
Can I ask one last thing on this? Thank you. And can you calculate the squared with amplitudes methods from the static?
This is what we did, more or less what we did in the last lecture. The only complaint that you could voice is that this I epsilon, precisely because it relates to, so this is really just calculated by using the formula that we showed today, but with this waveform, or waveform quote unquote, precisely because it includes these static modes, which are not really waves in any sense of the word, right? So you literally just do the calculation that we did today with this waveform, and you find the right result for the static one. In fact, it's even a bit nicer in the sense that it's non-perturbative in G. You find the order G squared, the order G cubed, and then modulo the inclusion of the linear memory, you can find the order G4, G5, etc. Just it's a much simpler calculation. So in a sense, yes, you can deduce it from Weinberg theorem up to cheating a little bit with this minus IX.
Okay, thank you very much.
Okay, any further questions?
Okay. Better thank Carlo for the